We've learned about definite integrals, indefinite integrals, and now in section 7.8 we want to learn about a particular type of integral called improper integrals. And it strikes me funny just the name improper, as if there's something bad about these, that they're improper, they're not as polite as the other ones or something, I don't know. Essentially, improper integrals involve infinity one way or another. Now, there's two types that we'll deal with. The first type of improper integral, the infinity is obvious. One of the limits, or maybe both of the limits of integration, are infinity. You might be going from a constant to infinity, you might be going from minus infinity to a constant, or you might even be integrating over the whole real line and saying integrate all the way from minus infinity to plus infinity. That's the first type of improper integral that we'll deal with. And the second one, sometimes it's really hard to notice that the integral you're doing is improper because it looks just like a regular definite integral. The problem is that f of x has an asymptote, a vertical asymptote. Not an vertical asymptote, but a vertical asymptote. Somewhere between a and b. Now it might be at A or at B, but it might be somewhere in between them as well. And so the infinity in that case is that vertical asymptote, the function is headed towards infinity. So either the function is getting really big or the interval that you're integrating over is infinitely long. Okay. So let's take a look at, well, first of all, a definition of this first type. And then actually within the definition you'll see why it's improper. If I'm doing an integral from a to infinity of f of x dx, if you think about how we defined definite integrals, we said, hey, you're going to do a sum where you're taking the interval from a to b, cutting it up into n equal length pieces, and then taking one point in each of those subintervals and evaluating. Well, the problem is when you try to divide this interval from a to infinity, right? Here's a, and infinity's clear out here somewhere. You try to cut it up into n equal pieces. How long is each piece? Well, generally delta x is b minus a over n, so infinity minus a over n. There's a problem here, and this is what makes it improper. Is that the definition of how you evaluate definite integrals using Riemann sums doesn't work. It falls apart here because you can't find a delta x because it would still have to be infinitely long. So what we do is we say, well, don't go all the way to infinity. Just go to some value b. So look at the integral from a to b of f of x dx. But then allow b to head off towards infinity. So then take the limit as b goes to infinity. So let's do an example of that. Let's try, how about the integral from 1 to infinity of 1 over x squared dx. Okay. Think about what the graph looks like. 1 over x squared. When x is 1, y is 1. When x is 2, y is 1/4, so pretty small. When x is 3, y is 1/9, so this is really coming in close to 0 here. And I'm integrating all the way from 1 out to infinity, so I'm trying to find this area underneath that curve. Now you might look at it and say, well, it's infinitely long, so how could it be finite? Well, actually in this case I think it turns out it isn't finite. I'm going to take the limit as b goes to infinity of the integral 1 to b of 1 over x squared dx. So that's an x to the negative 2. So it integrates to x to the negative 1 divided by negative 1. Evaluate between 1 and b. Take the limit as b goes to infinity. So this would be, still taking the limit as b goes to infinity. Plug the b in. So this is minus 1 over b. Plug the plug the 1 in, so this would be minus 1 over 1. So this looks like limit as b goes to infinity of minus 1 over b plus 1. Well, the thing is, as b goes to infinity, minus 1 over b heads to 0. Right? The bigger and bigger number you divide by, 1 divided by a big number is going to be really small. Granted, it's negative, but it's still close to 0. So this would be a little bit less than 1, but as b gets bigger, it's still less than 1, but not much less than 1. And the bigger this gets, the bigger b gets, the smaller this gets, and you end up just with 1. Okay. Now, so that area is finite. The area from 1 to infinity of this thing is finite. It's equal to 1. I want to point out that when I do these, I don't always write down the limit as b goes to infinity. But the way I would notate this myself is I just say this is the integral from 1 to infinity, 1 over x squared dx. So this integrates to x to the negative 1 over negative 1, evaluated between 1 and infinity. So this is minus 1 over infinity minus 1 over 1. And this right here, I write it this way, but I know that really what I'm doing is what I did up here. I'm taking a limit as b goes to infinity. I'm not really plugging in infinity. I'm plugging in bigger and bigger numbers and looking at what happens. Right? But the thing is, 1 divided by a big number is small, and essentially 1 divided by the biggest number is as small as you can get. That would be 0. Okay? So this would be 0 plus 1, which is 1. I will often write it this way, but I know that what I'm doing is this. There's times when it's not clear to me what happens when I plug the infinity, so then I really do have to go back and think about what's happening with that limit. And we'll see some of those examples. Let's do another example. Let's do a similar one. Actually, let's do the integral of, how about 1 over x squared from 1 to infinity. We just did that one. I meant the square root of x. There we go. 1 over the square root of x dx. Looks similar, but not quite the same. Still, when x is 1, y is 1. When x is 2, y is 1 over the square root of 2. That's 0.707. When x is 4, y is a half. Right? So this is still coming down to 0, but it's not coming down as fast as the other one was. So let's see what this one gives me. So this is an x to the negative a half. So it's an integral from 1 to infinity, x to the negative a half dx. So that integrates to x to the positive a half divided by a half, which would just be multiplying by 2. Evaluate between 1 and b, or I'm going to write it as evaluating between 1 and infinity. I'm just thinking of that as a big number getting bigger and bigger and bigger. So this would be 2 times the square root of infinity minus 2 times the square root of 1. Now, again, this is square root of b, where b gets bigger and bigger and bigger. But the thing is, the square root of, if you look at the square root function, the bigger number you plug in, the bigger the output gets. So this thing right here is headed towards infinity. And infinity minus 2 is still infinity. So what we say here, because this did not come out to be a finite number, I say that this integral diverges, that it's not finite. In the previous example where I did get a finite number, sometimes people would say, hey, this converges to 1, or you could just say it equals 1, but they use converge and diverge depending on whether you get a finite number, converge, or infinity, and hence the integral diverges. Okay. So that's the first type of improper integral, where you have an infinity in the limit. Next I want to talk about the other type of improper integral, but I'm running short on time here, so let's do that in another video.